Hello everybody and welcome to another physical sciences tutorial video. I'm very happy to be giving this video to you today because today we're going to be doing a very exciting topic. Okay, today's topic is Work Energy Theorem, alright, for the grade 12 syllabus. Alright, this is going to be very fun. This is a fun section actually to be doing because we can actually, after we've understood it well, almost always achieve or obtain full marks per paper for this section. In the paper, it's absolutely wonderful. It's absolutely mind-blowing, in fact. So we are first going to understand a few terms before we begin with actually going through work energy theorem. The first term we need to have a look at is net work. Now, what is net work? Right now, the net work on an object is the overall work done by a number of different forces being exerted on the object. Now, throughout physics from grade 10 all the way up to grade 12, we have heard the word net, and by now I'm sure we all know that net means overall or the total work, okay, when we talking about net work. All right, so net work is the overall or total work done by a number of different forces being exerted on the object. All right, now we do know what is the formula for work. Okay, we have looked at it in previous videos, I'm sure. All right, the formula for work is W equals to F, the force, delta X, and cos theta. All right, so we know that net work, if there's more than one force being exerted on the object, okay, then we can apply this formula where it would be W net, all right, equals F1 delta X cos theta plus F2 delta X cos theta, etc., etc. Okay, wonderful. So let's go back to our notes. There are two methods for determining the net work done, or W net. Okay, now the method one, the first method, is calculating the work done by each force. Now we know the number of different forces that can exist. We know there's the gravitational force, Fg. All right, in fact, let's put that down on our board. Okay, let's just get a clear spot here. All right, there we go. So we know there's a Fg, which we know is force of gravity. Okay, just going through this roughly, okay, because we already know, I'm sure we already know this, but this is just for recap, revision purposes. We know there's the force applied, Fap. You know, it's the applied force. All right, we also know there's a frictional force. All right, friction. All right, we also know there's a tension. All right, there's a force of tension. All right, what else do we know? We know there's different components of Fg. All right, we know that there's a Fg parallel, and we know that is a Fg perpendicular. All right, so those are a number of the different forces that actually exist. All right, so we can calculate the work done, and this is how we do it. First, we draw a force diagram of all the forces acting on the object. Then we determine the angle theta between each force and direction of the displacement. Then we use the work formula, which is W equals F delta X cos theta, to find the work done by each force. Once we found the work done by each force, we can add the work done by each force to obtain the net or total or overall work done. This is a great method to use and possibly sometimes one of the easiest, but before we decide that this is the easiest method for us to use, let's have a look at what is method 2. Now method 2 entails us calculating the work done by the net force. Now we draw a diagram showing all the forces acting along the plane of motion. So everything in our scenario, all the forces, we draw a diagram for it. So we can draw a free body diagram or a force diagram. A force diagram is possibly better. We ignore forces acting perpendicular to the plane because we know that if a force is acting perpendicular to the plane, there is zero work done on the object. So those forces would be, for example, those forces would be the normal force. The normal force. All right? Now the normal force, all right, and the force of gravity equals zero work done. There's no work done on the object. Okay, fantastic. Now, back to our notes. Now we calculate the net force, or F net, acting on the object parallel to the plane. Once we have done that, we calculate the work done by the net force. Okay, so then we use the formula W net equals F net delta x cos theta. All right. Now, once we have obtained the net forces of the plane parallel to the plane, it might seem simple to just plug that straight into the W net formula. Problem is sometimes people may get confused with direction of forces because friction is in the opposite direction to the force applied. All right, and it gets a little confusing when adding in the FG parallel component sometimes when adding that to the net force. So a method that I used when I was at school, I always chose method 1, all right, which was a little bit more calculating, but I knew that I stood a greater chance of getting my W net correct than on method 1 than I did on method 2. Okay, but you are free, of course, to choose your own methods when calculating W net. All right, so what we're going to do now is you're just going to have a look at a worked example for the last 3 minutes of this video, and then after we've seen a worked example and how they've calculated it using the two methods, okay, we can then determine what method we are going to use. Okay, for the purposes of the examples that are shown, I will probably 9 times out of 10 be showing method 1. All right, but here in the worked example we can see methods 1 and 2. Okay, so let's have a look at worked example 4 from the Ciavula textbook. All right. So approach 1, calculating the net work on a car. All right, so this is approach 1. The same car is now accelerating forward, but friction is working against the motion of the car. A force of 300 newtons is applied forward on the car while it's traveling at 20 meters forward. A frictional force of 100 newtons acts to oppose the motion. Calculate the net work done on the car. Only forces with a component on the plane of motion are shown on the diagram. No work is done by Fg or the normal force as they act perpendicular to the direction of motion. Alright, let's have a look at the solution. As always, we first analyze the question and we determine what information is provided. So they gave us the force applied, which is 300 newtons forward, the force of friction, which is 100 newtons in the opposite direction of motion, so backwards. The distance, delta x, was 20 meters, and the applied force and distance are moved in the same direction as the car, so they are in the same plane. So we calculate the work done by the applied force and the work done by the force of friction, which is backwards. And these quantities are all in the correct units, so we do not need to convert any components or convert any units. Step 2. We analyze the question. So we are asked to find the net work done on the car. So we know the work formula is W equals F delta x cos theta. Now, we calculate the work done by the force applied first, which is 300 times 20 times cos of 0, because delta x is in the same direction of motion as the applied force. Then we get cos 0 is 1 times 300 times 20, and the work done by the force applied in total is 6,000 joules. Then we calculate the work done by the force of friction. Now the force of friction, opposite direction, we know the force of friction was 100 delta x was 20. And because it's going in the opposite direction, our theta is now 180. It creates a 180-degree angle. So we know it's 100 times 20. Cos 180 is negative 1. And we get an answer of negative 2,000 joules. Now, the net force, or the net work done, the net work done on the car is equal to the work of force applied plus the work of the force of friction. That gives us 6,000 plus negative 2,000 joules, and that gives us the total work or overall work done on the car to be 4,000 joules. Alright? Now, the answer shown in this worked example shows that although energy has been lost by the car due to friction, the total work done on the car has resulted in a net energy gain. So therefore, this can be seen by the positive answer. Alright, so the net work was not negative, the net work was positive. So even though friction tried to slow the car down, there's still a positive energy gain in this question. Okay, now in the next video I'll be showing you method 2, and I'll also be showing you some examples and how to work through them by yourself. And method 2 in the next video will be showing you the same question, just a different method.